Okay, hello everyone, and welcome back to my R tutorial series. I apologize for a long gap between this video and the last one. I got really busy with my last semester of school, and this summer has been also fairly busy, so these videos got kind of shoved to the bottom of the to-do list, but I do intend to continue the series and move on with some interesting workflows and R lessons. This one I am going to use to finish the statistical workflow that I started with lessons 6 and 7 using the chick weights data set that's built into base R. And this time I'm going to use all 6 feed types. If you remember from the last couple episodes, I was using just 2 to show you what kind of tests you do for those and how to visualize those. This time I'm going to use all 6 factor levels or feed types and show you how to use those multi-factor pairwise tests and things like that. So this is going to be very similar to the statistical workflow of the previous 2, except it's going to differ a bit from the later on part of the workflow, the part where we tested between the 2 means, because now we're going to be testing across 6 different means. So as a disclaimer, I do advise you again, if you're brand new to R, to make sure you have at least watched my first 5 lessons, and also probably 6 and 7 if you're at this point in this workflow, but I'm assuming that you do know how to use basic code jargon and how the code is structured to some extent. As long as you know the basic commands and how to actually use R, that is going to be assumed, so make sure you do know some of that. Like I said in the last 2 episodes, we tested for normality using the horse bean and linseed fed chicks in the data set. We found that the data were normally distributed, and then we tested for significant differences. We found a statistically significant difference between the 2 feed types, and we plotted the final results with a box plot. Today, like I said, we're going to expand this to all 6 feed types that are present in the data set. And so to do that, I'm just going to start from scratch here, and we're going to call the data set in with the data command. It's just called chick WTS. Remember, there's another data set called chick weights. It's a little different. I'm using the chick WTS one. If we run that, it opens it up for us here. Actually, I'm not sure why it opened it that time. Sometimes it opens it, sometimes it doesn't. But you can see there's weight of chicks. Each chick was fed a different feed after, I think, 6 weeks of growth. Refer to episode 6 if you want to know the details of this data set, but there are 6 types of feed here that we're concerned with. One interesting command that I don't think I talked about before that is good for kind of just overviewing the data that you have is the table command. So this is useful to see if there are typos or anything in your data, because basically you give it a column in a data set. Usually you want to do this with a factor type column, such as the feed type. I wouldn't do this for the weight column because that's just going to give you a lot of stuff that isn't very useful. And basically this just shows you how many data points, how many rows are assigned to this feed type in this case, or how many different rows are assigned to this factor level. So when I say factor level, in this case I mean the feed type, but it's basically a category that you're comparing the means of. So in the previous workflow I was using horse bean and linseed. Those were our 2 factor levels. This time we have 6, and the table command will show that to us. So all we need to do is give it the feed column. So if you want to separate it out to its own vector, you can do that, or you can just use the $, or whatever other method you want to use for calling a specific column. But if we do that, you'll see now it gives us each of the 6 feed types and how many rows have that feed type. So they range anywhere from 10 to 14, mostly around 12. But that shows us the number of data points that we'll be comparing for each type. This is good for, like I said, detecting typos or other errors in data, like especially if you're bringing them in from Excel. I use this frequently to look for anything, like I said, a typo, or anytime that there's like a blank or an NA, and it can be a good method to find those things, especially in a larger data set. Or in this case, you can compare factor levels to see how equal they are in size, because that usually the more equal the factor levels, the better the tests will do at detecting differences. It also gives you the n, the number of data points. So if they're too small, then you're going to have difficulty with statistics. This is a very small data set, but it should be usable for what we're doing. So now that we've seen all that, we can actually get into the statistics. We're going to start by doing basically the same kind of stuff that we did in the previous one. We're going to start by looking for normality. This time we're just not going to subset it. We're going to use the whole data set of the weights data. So I am going to make a separate vector for the weights, just calling it WTS, check WTS $weight. I'm just going to separate out that column as its own vector, so you'll see it appears here in the values under the environment pane. There's 71 different weights, so that's how many we're comparing now, as opposed to the probably 30 some or 20 some. I don't remember exactly. I guess it would be 20 some. And now we can make a QQ plot. Remember, for details on this, you can refer to episodes 6 and 7 from my R series. I'm trying not to give too much duplicated information to save time in the videos. So to make the QQ plot, again, we use QQ norm to generate the actual data points on the QQ plot, and then we use QQ line, and we're just using the weights as the argument. So if we run this whole chunk, it will plot these together. We've got the data points and we've got the line. The closer the data points are to the line, the more normally distributed the data is. So this looks quite good for a QQ plot. The tails are always going to go off to the sides a little bit, but this is really close. This is really solid. So I would expect that we have a normal distribution here just based off of this. Of course, we can also make a histogram with a normal bell curve overlaid on it, just like we did in episode 6. So to make the histogram, we use the hist command on WTS, and then we can add a title using the main argument. Main equals, we'll call it chick weights, if I can spell weights. Remember, all of these are optional. Really, the only thing you need is where it says weights here. But I like having just a little bit of stuff just to make sure I know what I'm looking at. We can give it an x-axis label using xlab, and we'll just call it weight in grams. Now again, you can also have space or not have space. That's up to you. I like to have space. I like to put them on separate lines. You don't have to do any of this. You don't need any spaces after the commas or between the equal signs, as long as you use quotes where they are needed and commas where they are needed. Those are the more important things. So we'll close off that. Let's take a look at our histogram. That looks pretty normal to me, even without the bell curve. I'll show you once again how to make the bell curve, though. So at this point, we can make a vector called xvals, short for x values. We're going to use the assignment operator, the little arrow symbol. And we're going to just make a sequence using the seq command, S-E-Q, starting with from. So this is the starting value, and we want to use just the minimum and maximum value of the weights data. So we want the lowest and the highest weight. So we'll use min for minimum of WTS. The next argument is 2. That's the end point of the sequence. Max of weights. And then by is just the interval. So we'll just use 0.5. That should be fine. Give us plenty. Basically, we're making a discrete points that are going to look continuous on the curve. So the 0.5 is just how far apart they are. So then we'll use the lines command to add to our histogram, which means we will need to run this entire code chunk once it's all finished. So the x is just the x values of the weights data set, from our sequence. So x is x vals. That's the x coordinates of each point on the line, by the way. And then the y, we need to generate a normal distribution based on the weights data. So we're going to use dnorm to generate that distribution. And then in the dnorm command, within the lines command, the x again is going to be x vals, because we want it to follow those values to cover the entire data set. And then we just give it the mean of the chick weights, so mean of WTS, and then the standard deviation, just SD, also SD of WTS. So again, you can put them on separate lines if you like to make it easier to read. That will close off the dnorm argument, but it'll also close off the lines command. So you can do it like this if you want, however you like to do to organize your data. You can have it all on one line. It doesn't matter as long as you've got the right parentheses and commas and everything like that. So now, if we run this whole chunk, oh, I did forget one important thing. Okay, so the standard histogram is made using frequency. We actually want density. So I forgot about this. We need to put in our histogram command needs to have freq, F-R-E-Q, equals false. It can just be F, capital F, or it can be the full word false, as long as it'll change colors depending on your color scheme here. But we want it to not be using frequency. We want it to use density. Now we can adjust the y limits using also in the histogram command. We can use ylim to make it so that we can see the whole bell curve. Not totally necessary here, but let's just say 0 to 0.008, just so that we can see the whole thing. We'll want to concatenate this using the C command, 0, comma, 0.008, and then another parentheses. Now that raised our limit. We probably could have done 6, but that's fine. That looks pretty normally distributed to me. That normal bell curve is a hypothetical normal distribution based on the mean and standard deviation of the actual weights data. So therefore, this is what it should look like if it was perfectly normally distributed. It's pretty darn close. That's a pretty good normal distribution. But let's check the statistics anyway. Now, I'm going to refer to lesson 7. And you can see I've got this whole code chunk written out. This is just code that I leave copy-pastable, available anytime I need to run normality tests for any kind of data, and then all I have to do is change what I'm actually testing. So remember, you do need the package nor test for some of these, maybe all of them. I don't remember which ones are in it, which ones aren't. But we can use library. You can also use require if you prefer to call that package. And then you may just want to pause the video to copy this, or if you were following along with lesson 6, you could copy paste that. It's the same exact code because I'm using the same object name. The only difference here again is that it's not subsetted to those 2 feed types. I just kept all 6 in WTS, but it's the same exact code. So this will give us a nice table of them. Alternatively, I don't remember if I explained this in the previous lessons, but if you wanted to only run one test at a time, the commands to do so are just this part of each line. So the Anderson-Darling test is ad.test, and then your data. Likewise with Kramer von Mises, it's just cvm.test, lily.test for Kolmogorov-Smirnov, etc. So you can use any of these if you prefer. Or you can just use all of them like I am. All this extra stuff is just to make the table look nice. So the tests just give you the row names. The assigns this name to the test. And then this 2 in brackets pulls the p-value directly out of the test. So it gets rid of all of the extra numbers that even I'm not sure what they actually represent in some cases. And then this data frame, these 2 lines here, make it into a nice table. So if we run this whole chunk, we'll get these nice names and p-values associated. So if we remember, I'm using just the standard alpha value of 0.05. That's what I think most people use that. And the null hypothesis of these tests is that that the data is normally distributed. So if the p-value is above alpha, as it is in all of these, that means we can assume that the data is probably normally distributed, at least according to these tests. Once again, p-value statistics are not always ideal, but they are currently what pretty much everybody uses, and in most publications or journals, they would want p-values for your statistics. So therefore, we are assuming that this is normally distributed, as is agreed by our plots up here. Now we can check for the equivalence of variance. In the previous lessons, I showed you the Levine test and the Bartlett test. I'm just going to use the Levine test here. I believe the Bartlett test is better if your data is very strongly normal. For me, I think that usually means the p-value above 0.5, but I may be wrong on that. Again, I'm not a statistician. So feel free to use either one as you wish. The Levine test is found in the car data package, so we'll just need to call that in. And then the command, again, is Levine test with a capital T. That other option that comes up, Levine.test, I think is deprecated, so don't use that. But this Levine test just requires, in formula format, the numeric data, tilde, and then your factors. So in this case, the feed type. I have a document that I'm just copy pasting this from, but you're welcome to pause the video as needed to follow along. So we're just going to test the weight versus the feed type. And the p-value, this is kind of ugly output, but the p-value is this second number here, this, I guess, last number on the right, and it's 0.58. Again, the null hypothesis here is that there is no difference between the variances, so this means that the variances are equal, at least statistically. So, with normal distribution and a equivalence of variance, we can use parametric statistics. Now this is where it gets a little different from our previous workflow because we're using more than 2 factor levels. The t-test is made for 2 factor levels by default. I believe there is a pairwise t-test, but that's also basically an ANOVA test. So ANOVA stands for analysis of variance, and basically it's just a t-test that's been generalized for more than 2 factor levels. So to do that, it's a little different of a format because of the way the code gives you output. The ANOVA command is just AOV, and it's in the base R package, the stats package, so you don't actually need to call any packages for it. And we just give it the same exact format as the Levine test here. However, for this, we want to save it as an object. So I'm just going to call that object AOV. Give it the assignment operator. This is because it doesn't, for some reason, the default output does not give you a p-value. And we want the p-value. Now, of course, this is testing all the different feed types, but how does it do that? It does it in a pairwise fashion. And what that means is it tests every pair of factor levels against each other. So it'll actually give you quite a few outputs. There's 6 feed types, so it's testing all of those against each other. So that's going to be quite a few p-values. I don't know exactly how many, I can't do that off the top of my head, but we'll see here in a moment. So let's run this, and all that's going to do is create an object. It gives us 13, that's our number of p-values. And you can see it's a list up here in the data section of the environment pane. And to view the p-values, the easiest way to do it is to use the summary command on the object that we created for the test. So summary of AOV, this gives us a p-value overall of this very, very small number. It's this PR value. And R even tells you how significant it is based on your alpha, so it's extremely close to 0, which means it's very significant. That means that there is a difference in at least one pair of the feed types. This may be all of the feed types are significantly different from each other, or it may be just a handful, or it may be just one pair. We don't know from this. Now, the best way to find that out is to use a separate test to test for pairwise differences and get actual p-values out of it. So if the data is normally distributed and you have equal variances, we use a test with a very fun name. It's called Tukey's Honestly Significant Differences Test, also known as Tukey HSD. So the actual command is also in the stats package in R, so you don't have to call anything. And here's the command, Tukey HSD. And we just run this on the AOV object that we've already made. And now that will give us all kinds of information. So this final column is PADJ, that stands for p-value adjusted, or adjusted p-value. And the p-value null hypothesis, again, is that there's no difference. So if it's lower than our alpha of 0.05, that means there is a significant difference. So if it's a 0 like this, that means it's so low it can't even be calculated. That's a pretty significant difference. There's a few that are not significant here. So meat meal versus casein is not a significant difference. Sunflower versus casein basically looks like the same. So 0 difference there. That's a very, very high p-value. Linseed and horse bean is a pretty low number. That's interesting. Didn't we compared those in our first one and we found a significant difference. It's interesting. Sometimes different tests give you different results. Anyway, most of them are significant with well, maybe half of them. Half of them are significant and half of them are not. Either way, we have a lot of differences. This is pretty ugly. It's hard to read. And we'll want to visualize it with a plot to make it much easier to tell the actual difference. So again, we can use a box plot. So very simply to start, I always just try to get everything visualized in a rough format for myself so that I can then change the aesthetics. And again, we can just use the same format as we have for the last couple of tests. So in the formula format. You can also say wait tilde feed and then use the data argument to say chick weights, as in that's where the data is coming from. But since I already have it here, I'm just going to use this. So that's currently not very visually appealing, not very nice to look at, not very well organized, but it gets the point across. And since I'm running out of time for this episode, I'm going to leave it here. But then in the next episode, I'll use that to show you how to thoroughly manipulate your plots in R. And we'll use this plot as a baseline to make it look pretty. There's a lot of different formatting things that we can change on box plots especially. We can also add a strip chart to show the actual distribution of the points, which I like to do. We can change colors, change the format of the axes, all kinds of things. So I'll leave you with that. If you're interested in more, please feel free to subscribe. And if you have requests or suggestions or something to correct about my statistical knowledge, feel free to do that in the comments. Again, I'm sorry for the gap in videos. I do plan to post more very soon. Thanks for watching, everyone.